Welcome, Wu Yang. Wu Yang is the Technical and Foundry Programs Manager at Siemens EDA. With more than 20 years of experience in DFT, silicon learning, and testing, Mr. Yang has been a frequent speaker at many conferences and a regular contributor to papers and articles. He's delivered multiple tutorials at ITC, ATS, ETS, and VTS. Mr. Yang received his MS degree in electrical engineering from Portland State University. So please welcome you.
Okay. Hello, everyone, and great to have this opportunity to discuss with you for the 3D IC test challenges, trends, and the solutions. Since I come from the Siemens EDA, one of the EDA companies in the world, so I'd like to express our ideas, opinions from an EDA perspective. So here are the contents for this talk. We need to understand 3D IC market and the test challenges in order for EDA company to develop the right solutions. Because we have recently the new I2B standard approved for 3D IC testing, I'm going to touch a little bit of it so that we have a better understanding the pros and cons. Then we talk about 2.5D and 3D test methodologies and draw a conclusion. So since last year, we talked to a lot of customers, tried to do a market survey to understand where we are in terms of 3D test challenges and in terms of production stages. It is very interesting. We found that to some extent that 2.5D 3D for the test methodology side, they could be similar. And in terms of details, there are still a lot of differences. For example, for 2.5D, they are in production already. Basically, we're talking about lateral die putting side to side on common interposer versus 3D, where the die stack on each other. And in terms of DFT, for 2.5D, you may have more DFT pins accessible at a package than that of 3D. In terms of requirements, if you look at the details for 2.5D, for example, a lot of die, or maybe for each individual die in the package has the boundary scan, so that customer told us that they looking for a cross-die 1149.1 compatible tab. That is different from the 3D, because for 3D, for the die embedded, you don't have the boundary scan because it's too costly if you put too many boundary scan over there. And also, since you have boundary scan for 2.5D, you could have the BSDL for each individual die. And you like to have the BSDL-based die-to-die test pattern generation. So all those, you can see they are unique, and they are different from that of a 3D testing. In terms of 3D, since you have less DFT pins accessibility, so that you have to consider strictly following the standard. For example, you have the primary tab, a secondary tab talk to each other between the dies to make sure you have a serial interface and a parallel interface. So I'm going to talk more in the details in the next few slides. I2B 1838 as a standard is being released last year. This standard addresses a standardized die DFT infrastructure for inter-die integration and provides the hardware and the protocol standards. So in short, this standard has three basic components, the critical components. One I already mentioned about the serial port, right? Since here you have the tab, basically you have enhanced the tabs to consist of primary tab and a secondary tab. For between the die, the secondary tab is going to talk to the primary tab and next die, keep on going. So this serial port is mandatory based on the I2B 1838. It's used to help for die-to-die communication and can manage, for example, bypass of die or stacking. The second critical part is called the DWR, the die wrapper register. Because once you stack things together, a lot of pins cannot be accessible from outside. You have to find a way to wrap the die so that you can facilitate die-to-die communication, especially for die-die testing. The third one is called optional flexible parallel port, FPP. Here is pretty much the bidirectional, the one way in, one way out, and also can go into left or right in between the die, inside the die. So this interface is to provide the scan data in and out of this stacking. However, the 1838 doesn't differentiate requirements between 2.5D and a 3D, as I just introduced briefly in the previous slide, and does not provide an operation language, and does not discuss how to do DFT and test. As an EDA vendor, you have to consider all this, right? We are facing all the users who are engineers. They need to make things happen. They need to actually design the chips and be able to put on the tester for testing, and also have considered the automation, the test costs, etc. Many things have to be considered. So from the solution point of view, developing a 3D IC testing is not going to start from scratch. Instead, you are going to have lots of existing technologies to help you enable 3D IC testing. So at Siemens EDA, for example, we have a suite of different methodologies to make things happen, right? You have the logic test, memory test, how to make sure that all the bits can talk to each other, talk to logics, etc., etc. And also you need to make sure that the safety, the full side related to DFT and test quality, everything has to be in place. And once chips, they are in silicon, you need to find a way to accelerate the first silicon debug and also to do the yield analysis to help you ramp up their production. And another important thing is you have to find a way to integrate everything together so that you operating the DFT management, everything is on one platform to make things happen. This is automation. And another two critical technologies I like to mention a little bit here is, one is the plug and play IJTech infrastructure. It is I2B 1687 compliant IP. It is very important. You can see that in your whole designs, regardless from the chip level, inside or sub-chip level, or package level, you need to find a way to actually manage the whole DFT network. For stacking, you have so many different cores, dies with a different IP with, for example, the IEEE 1687, the PTAP, STAP. Those are the IPs. How you are going to integrate everything together? How are you going to set up everything easily? You need a language, you need a network to operate that. So that's the reason the 1687-based compliant IT network is a great vehicle here, mechanism here to make things happen. Secondly, with the newly announced technology called a streaming scan network, that's another way to help you design the flexible parallel port. So for this technology, basically, for example, you have so many cores inside the die. So this is just one die, right? So this technology is an N-bit-wide high-speed SSM bus called a stream scan network bus for sending the packetized data in and out. All the DFT signals, they are created at the die level, the core level, so that you can send in data to each individual core, and actually this idea can be extended to multiple die cases. So this kind of bus in, bus out can be well extended to other dies as well. So that is the base of the I2B FPP port support. And it gives you a lot of benefits, like save the DFT development time because you do everything here locally here, then you just put everything together. Can do a lot, give you a lot of flexibility for routing and time coder, and save you a lot of time and volume reduction, test volume reduction. and have a low ping and low power. I'm going to talk more about that in the 3D stacking. So let's talk about the 2.5D DFT methodology. In this case, we have to look from 4 different categories, different aspects of this challenge. What is the DFT infrastructure? What are you going to do with the wafer level die test? What are you going to do for the die test inside the package? And how to do die-to-die test? On the right is the methodology and infrastructure for 2.5D. So at the bottom, those are the existing technologies like hierarchical DFT. You know that regardless you are doing the die test at wafer or die test in package, in order to facilitate the easiness of your design, you create the patterns at core level, right? Then you find a way to retarget the patterns to the die level so that you can perform the die test at wafer. When you put the die together into a package, right? So this core pattern can be retargeted to the die level and all the way retargeted to the package level. So all this you need hierarchical DFT. This is true not only for BIST, for all kinds of DFT IPs, ADBG, etc. Secondly is the streaming scan network. Okay, so in this case, you see that if for 2.5, each die has its own boundary scan, so that you do not need to have I2B 1838 serial port, that kind of a P-tab, S-tab, because you can just simply connect your existing tab together in a cascade chain so that you build a 1149.1 compliant tab to facilitate your package level testing. And the scan data in and out, you can utilize the streaming scan network. So you can see the big difference here is you're sending scanning data to die 1, go through each individual core inside the die and the top level of this die. Oh, sorry. Then it comes out. So this, you do not need to come out directly to the package. You can actually just send in to the next die, continue doing that. If you do not have this technology, you have scan data coming, scan data has to come out. Then you have another scan coming to another die, scan come out. So you're going to waste a lot of I/O areas. Again, all the operation, everything is managed by 1687 compliant IJTAG. The tab and how the die types talk to each other, boundary scan, hook up to the IJT network, everything can happen. Of course, talking here is simple, but actually when you implement it, things happen. You have to consider the standards I just mentioned. Also, you have to make a lot of new advancements because when you do actually engineering, you find a lot of things not seen before. So that's the reason that lots of enhancements are being done to make sure that all this structure works. All the IJT network can work with things seamlessly without a problem. So in terms of wafer test, I mentioned that already. So basically, in this case, some people may design sacrificial paths, some people may not, because for 2.5D, you have a much more area overhead you could tolerate, so that you may have all their, those IOs could be programmed by IT, but if not, you need to design the web cells to make sure things can be well contained within the die. And for the die test in the package, so as I mentioned, you utilize the hierarchical DFT methodology. You can just retarget the core all the way to the package level without any problem. And for die-to-die test, since each die may have its own boundary scan, so that you could do BSDL-based die-to-die ADBG, but that is limited to the StarGap test. For speed, there is many more different ways to do it. So, for example, you could build a die-level gray box to do die-to-die ADBG. Okay, so that is about the 2.5D. Now about for the 3D. So 3D has a lot of new challenges. First, you don't have many pins can be accessed from the package level to reach out to inside the die. Again, there's still 4 categories you needed to consider in terms of making this 3D methodology happen. Similar to 2.5D, you need to have hierarchical DFT, stream scan network, and IGA network to operate the whole system. So in this case, you can see the 3D stacking here from the very high level. It looked a little bit similar to 2.5D, but there are lots of differences. First, the serial port needs to consist of, needs to use the I2B 1838. So you need to have the P-tab, S-tab to make all the connections. And all those from the implementation point of view, the P-tab and S-tab could be modeled as ECO and PDL of the IGA network, IGA network language, so that they can be easily integrated to the IGA network for across the whole die. Second, for the structure itself, you can see that when we talk to lots of customers, for 3D stacking, they may have boundary scan, only one side towards the packaging side, they may have the boundary scan. But for the other side and all the other die, they don't have boundary scan because it's too costly if you put boundary scan in. So in this case, and for the testing purposes, there are a few things to be considered. For example, when you do a die-wafer test, you need to have a sacrificial path built up. Because in this case, you're only going to have a couple of IOs, like JTAG IOs and the FPP port IOs and maybe clocks being probed by the ATE. Then all the other IOs, you need to find a way to wrap them. This requirement has one important factor is because when you do die at a wafer test, you want to make sure that this type of a patterns is going to be the same pattern when you test the die inside the package. Because of that, you have to make sure that all those die, the IOs, except for those DFT pins, being wrapped. So once you stack them together, the sacrificial paths will be discarded. And you just push them together and everything will operate like inside the package. So you have to use the I2B tab, 1838 tab to do the management and use the flexible parallel port to sending data in and out. So in this case, you can see that if you use the streaming scan network, SSN technology here, it gives you a lot of benefits. One is, for example, this data coming, going to each core, going to the top level of the die, and go to the next one, go to the next one, and coming back. So this bus can be as wide as, for example, some customer told us 128 bits in, 128 out. Or you can use as little as just 1 in and 1 out. It's very flexible. And some customers even consider, why not just share that in and out with TDI, TDO? So you don't need to have the dedicated FPP pins. Second, for the management, because you have IGA network, SSN, and all the IPs organically managed together, it's very easy to set up. So for FPP, for example, you can arbitrarily select a combination of cores to be tested together. For example, in this bottom die, you pick core BB, the middle die, you pick core UA, and the top die, you pick core AA. All the 3 cores can be tested together, just use one SSN bus to manage that and make things happen. This gives you a lot of flexibility for managing the power. And also another benefit is you may have lots of identical die, right? Oh, sorry. So once you put lots of identical die, there are many things the FPP can help you. One is you do broadcasting. You have lots of die stacked on top. You just use one bus and this bus broadcasting to each individual die to make things happen. And secondly, If you have so many die, you do not want to store so many patterns at the package level, right? Because if you have one die, you retarget the pattern to the package level, then during test, you apply that pattern, right? And you have a different, if you have a different die, you may have retarget again to the package level and store that pattern somewhere and apply on a tester. It's very costly in terms of storage. In this case, you could just generate one set of patterns out of the one die, one of the identical die. Then at the ATE level, you just patch that pattern, make things happen. Because they are all identical dies, the difference between them is the latency or some other simple setup. So SSN can make things happen like that. So in terms of die-to-die test, since you build rep cells already for each individual IO, including TSV as you need it, so that you can build a gray box for this individual die, then you can do die-to-die ADPG. And of course, for 3D, there's lots of I2B standards you have to meet. 1838, 1687, and 1149.1, 610, because you could use a high-speed I/O to support FPP to increase your shift-out speeds, and I2B 1500 for handling the IPs, etc. So I like to emphasize a little bit on the die-to-die test, because that's that is the common topic our customers ask us to put together a solution for them. In short, the die-to-die test consists of three things: low-speed test, S-speed test, and high-speed test. And let's take a look at the right picture here. So this is the chiplet. Each die has its boundary scan. And back in 2019, Jurenic, so he had a presentation at the BRS Test Symposium talking about how to do the die-to-die test utilizing the BSDL-based solution, since you have each individual boundary scan so that you can have a BSDL. Then you have BSDL to BSDL, you can perform the pattern generation. So we are in the middle of making that automated. However, the problem is that is just one of the scenario. But in the real world, if you look at left picture, so here represents the package consisting of two die. And this idea can be well extended to the stacking case. So you can see here on the right, I just use one example. When you build the DWR, the die wrap chains, the cells consist DWR is quite complicated. They could come from the block wrap cells or the scan cells of this die top, or even potentially come from the boundary scan if you have one. Even I talk to foundries, to a lot of customers, we prefer not to have any logics between the IO and the DWR. But the reality is you cannot prevent them from doing it. Some people have to do that due to many different reasons. In this case, you can see that this DWR is much more complicated than just a boundary scan, so that the BSDL-based die-to-die test no longer works. Also, even for the BSDL-based, how are you going to perform S-speed test? You can't. So that's the reason you have to build the DWR-based gray box of this die to do die-to-die test, because by doing this, you can test logics between the IO and the DWR. We're familiar with the hierarchical DFT, right? For example, in hierarchical DFT, you have in test for block level test, X test for the logics outside the blocks. But in this case, it's different, right? It is totally different. This DWR comes from a variety of different cells. So we have a total new test mode to make things happen. So we already made that happen. In this case, both low speed and speed test can be utilized this die-to-die based gray box testing. And another benefits of doing that is, once you do ATPG, you are going to have automatic diagnosis solution. So you can do diagnosis inside the core at die top and between the die without a problem. Also true for that speed. And for the high speed, because people usually talk about SerDes, in this case, for these IOs, they have the customer IO or function IO for IO based. Now, as long as you just hook up those IO based to the IGT network I mentioned before, then IGT network is used to manage, capture, set up all those IO based testing. One thing you can do, well, the thing you do is you just pretty much retarget the IO based pattern all the way to the package level through the IGT network. Okay, so let's talk about all those logics. And there's a very common usage scenario is with external memories. I forgot to mention one thing here. So in this 3D flow, if you have a memory-based, you have a memory-based embedded in each core, and the memory-based or logic-based retargeting to the package level, there's no difference than you design a single die. Because as long as you provide IGT network, the memory base can be natively retargeted from the core level all the way to the package level, regardless of how many hierarchies you have over there. Very straightforward. So once you have this kind of external memory, for example, on the left is the base die, on the right is the HBM. And you take the HBM with the 1500, I2B 1500 interfaces. There are two things you can do here. One is for this HBM, you may have a embedded memory base already. So that this PHY through the 1500 interface to the base die, as long as you can hook up to the IGT network, what we can do is just retarget whatever you want to do, the patterns, all the way to the package level. The other thing you can do is, some of the people mentioned that the embedded memory base may not be sufficient enough for test quality requirements. So they like to implement the memory base in the base die so that you can test all the speed, all the passes from here all the way to the HBM at speed. In this case, as long as you build a memory controller, you can just switch in between the functional paths and on the SoC memory base. Everything should be fine, and you hook up the IGT network. And people may ask where you are these days for the solutions. And recently we have attended quite a few conferences and work with our partners. So one thing you can see, there is a special session proposed at the ITC, and we have a few people presented all the 3D-IC solutions. So this one is from Jeff Rick and AMD, and this one is from Sandeep Gokar from TSMC, and I also presented over there as well. And just about 2 weeks ago, Siemens and TSMC announced that reference flow for their 3D-IC in terms of DFT. So we have the 2-die stack, and we implement I2B 1687, 1838 IPs, and to fulfill all the related tests I just mentioned above. As a conclusion, and the 3D-IC test solution is built on the existing solution technologies and lots of new advancements, like a hierarchical DFT streaming scan network, IGTech. They provide a solid foundation for 3D-IC. And there are new standards like 1838 is in place that requires a lot of new enhancements to make sure that all the network, everything integrated together works. And we have built a reference flow with the top foundry so that we are enabling the ecosystem. On the other side, 3D-IC is a moving target. As Adam just mentioned about how to do heterogeneous die support using different DFT vendor solutions, right? All the things I mentioned above is utilizing the Siemens EDA DFT solutions. So how about what would die come from our competitor, a third party? How you make things work together? Also, if you have the die coming from different technology, 7 nanometer versus 12 nanometer versus 3 nanometer, how to integrate them together? how to do the interposer test during stacking, right? This is still a common question coming up. And how to do, for example, redundant I/O, and then integrate repair requirements. So the bottom line here is we need to call for an all-industry collaboration to enable 3D IC ecosystem. We're looking for partners to work together. We're want to build more sophisticated reference flows and define the standards to talk to facilitate die-to-die communication, not only from hardware, but also from network integration, also from the, for example, data exchange, etc. So that concludes my speak. Do you have any question?
Thanks, Wu. I think we've got time for maybe a question. So the question is, if after, a 3D IC product fails, during the manufacturing flow, not only do you have to figure out, which die is the problem potentially, but, there could also be problems with the interconnect itself. So how do you suss that out, or what are your thoughts there?
Sure. And I use this one as example. Since once you use the hierarchical DFT, it is a great way to do their diagnosis correspondingly. So for example, if you see a failure at the packaging level, and you are going to bring that failure file with the design information, you can do reverse map all the way to each individual die level, or even down to the core level. Even you have multiple hierarchies, you can go to deeper to the subcore level, because the pattern generated is the automated, and the diagnosis is automatic naturally. And for the die-to-die, since you have this gray box is perform die-to-die test, diagnosis is also natively supported. In this case, you go through this kind of reverse mapping, you can find out where this IO has a problem, or that the TSV has a problem. Similar idea for the BIST, memory BIST as well. So you just have this packaging level information, reverse map all the way down, so that you can perform that diagnosis.
Yep. In relative isolation. Got it.
Yeah.
All right. Great. All right. Thanks, Wu.